What tells us how quickly a ball accelerates down a hill or how fast heat spreads through a plate? By the end of this video you will see the Laplacian as the second derivative in space that measures the rate of change of the rate of change. Start with one dimension. The first derivative gives the slope, telling you how fast the height changes as you walk along x. Take the derivative again and you get the second derivative, the curvature, positive where the graph cups upward, negative where it cups downward. In two dimensions we list the first derivatives in x and y as a vector called the gradient. Its direction shows the steepest uphill and its length shows how steep. Now ask how that steepness itself changes. Take the divergence of the gradient, add the second x derivative to the second y derivative, and you obtain the Laplacian, a single scalar at every point. Where the Laplacian is large and positive the surface looks like a bowl opening up. Where it is negative the surface bends down like a dome. Imagine a drop of dye in water. The diffusion equation says the concentration changes in time proportional to the Laplacian of the concentration. Where the Laplacian is high the dye speeds up its spread because the slope of the concentration is itself changing rapidly, pushing material away. The same operator appears in the wave equation for a vibrating drum. The acceleration of the membrane upward equals the Laplacian of its height multiplied by a tension constant, so curvature drives motion. Diffusion smooths peaks and valleys, while waves oscillate because the Laplacian keeps nudging each point back toward flat. Remember, the Laplacian is simply the sum of second spatial derivatives, telling you how fast the slope itself is changing. Whenever you meet diffusion, heat flow, or wave motion, look for this operator. It is the mathematical engine that turns curvature into acceleration. Generate your own educational videos for free at eduvids.vercel.app.